Welcome to the Alien Scientist Science and Controversy Hour. I'm your host, Jeremy, the Alien Scientist. Today we're going to be talking about sort of an extension from last week's discussion. I'm bringing my special guest Ken Griggs on again, the quantum gravity theorist, um, to be talking about. I really wanted to talk about a different type of this book, specifically this book by Stephen Wolfram and some of the ideas that he put forward in it. It's called A New Kind of Science. And we're going to be talking about that whole idea of a generating function that maybe physics as we know it, that we've sort of developed the modern physics that we have from these theories of measurement and trying to fit measurement to a theory. That maybe there's a backwards approach that we're not really understanding. Maybe that as we look at this universe, we're really looking at the intricacies of a fractal and sort of trying to figure out the rules that generated that fractal by measuring things in real time and making physical laws for them. But maybe there's a function behind that that's generating this universe and generating things that maybe that the real physics that we need to understand are sort of hidden in this generating function that's creating everything and producing it out of it, and that we're never going to be able to get to that generating function or a theory of everything just from simply looking at laws of physics or taking measurements from our machines and looking at physics the way we're currently looking at physics. So we're trying to step outside the box and look at new types of physics, new ideas. I cover a lot of different stuff on this show: science, and controversies, conspiracies, anything that involves science that's sort of on the cutting edge or on the fringe. And as usual, not everyone's going to agree on everything all the time. So just keep that under advisement that our sponsors or the guests we have on from week to week don't necessarily agree with all the topics or what's being discussed on the show. Again, just a disclaimer that I have to throw out there at every episode. So anyways, we do this podcast every Saturday, 4 to 5 p.m. So if you're interested, that's Eastern Standard Time. If you are interested in calling in, asking questions, or asking for anyone who wants to call in, you're welcome to call into the show and pose a question. You can call into zenlive.tv or me, Alien Scientist, here on Skype from 4 to 5 p.m. There's also a studio call-in number that's only live during when we are showing actual air times. So if you want to call and get in on the show, ask a question, throw an idea out there, mention something, you're more than welcome to do that through those venues. And also recommend guests and hey, even be guests on my show. Like Ken was just a guy who called into my show, and I've been having him on every week with me because we're getting some interesting discussions going on about physics and real theoretical physics and science that are really outside what you normally find on YouTube when you look around for this type of stuff. I mean, you find some good stuff, some stuff's all right. I mean, this is maybe a little bit, we go on the technical side a lot. I try not to go too deep into the math because I know that loses a lot of people, but at the same time I try to bring it back to basics and break it down for a level that I know that general audiences can sort of follow along and think about quantum physics and just the theory of what's behind this universe that we are all a part of. But anyways, on that note, we're going to talk about this Wolfram Alpha and this new kind of science. I just uploaded some pictures to our producer there in studio at Zen Live TV, who's producing a show for us. So he's got a whole bunch of pictures in front of him of stuff I wanted to talk about. I don't know where I wanted to start, but I guess when we're talking about fractals and sort of this whole idea of that the universe could be a giant fractal, or that different parts of the universe seem to look fractal in nature, we have to look at other things that are fractal in nature to sort of compare them to what our models or our theories of physics are, and to sort of give us an idea of how we are to create a unit cell or a crystal that crystallizes itself to create every point in the known universe. Similar to this theory that we had discussed last week. Of course, we got the word wrong. It's actually monads. and monadology that Leibniz had thought up. This idea of this single point of all creation or all existence, and that the idea that the laws of physics are the same everywhere in the universe. So if you were to say at this point, the laws of physics are the same as at that point, and you have to sort of come up with a theory that can explain how the whole universe can be there, but still have this everything be conserved. And as we've learned through other theories of physics, such as laws of conservation and relativity, that not only is that point in space, but also even moving objects, even moving points in space are translational, and all the laws of physics are retained in those systems. Just as relativity, the speed of light is the same to all observers, no matter if you're going 100 miles an hour, or if you're standing still, or if you're going hundreds of thousands of miles. So this is sort of the basis idea that any point in the universe, the laws of physics are such, and if we were to understand them, then we could basically find new ways to manipulate them, or find new physics, new energy sources, new propulsion technologies, new types of a whole new realm of science that's about to be unlocked within probably our next 100 years of physics. I think we're on the cutting edge of a lot of things in physics at this point, and definitely this new type of science that's discussed in Stephen Wolfram's book. There's also an iPad app where you can do some of these generating functions and play around with a lot of this stuff. He creates a lot of interesting things. But in chapters 8 and 9, I think, are my favorites, where he really relates a lot of different patterns to things like leaf structures. He shows that you can get these arrays that look very, very similar to leaves and other natural objects in nature. He has a whole several pages on snail shells, that different generating functions that generate snail cells. And really, I would think that a lot of biological systems in nature probably follow very similar mathematical algorithms to produce whatever they're producing, or however it's being built in real space. It follows some sort of additive rules or algorithmic rules, which cause it to create these shapes in nature that we see, which are really, it's really fascinating stuff. But the whole idea is that maybe physics could benefit from this. In chapter 9, he discusses a lot of stuff in that book about physical theories of everything, and that basing a theory of everything on this idea that we have a fractal and a generating function that's actually creating the laws of physics, or creating the universe as we see it, creating either holographic dimensions of space and time, or creating whatever it is. And lots of laws of physics, like laws of conservation, as we pointed out in another episode. It always found it so interesting. Newton's second law of every action is an equal and opposite reaction, so that at every point where there's a force, or any object acts on another thing, there's always balanced forces, so that nothing ever really happens. It's only relative to something else, if you were to look at a bigger picture of things. Although lots of different things happen irreversibly, and you have thermodynamics and glass shattering and other things that don't really go backwards as much as they or don't tend to go backwards very often. I don't think they ever do. But basically, this whole idea of the unit cells, and I wanted to relate it a little bit to crystallography and crystals, because what we're learning about, just there's so much science that's going to come out of this in general. What he's discovered with these arrays and these generating functions, the science that he's discovered, has so many different applications, and one is going to be in crystals and in material science, and the production of crystal cells growing computers. Basically, like all our computers of the future are going to be based on photonics. They're going to be crystals that transmit light, and it's going to be pushing photons around instead of electrons, and there's going to be different things that happen inside these crystals. But they're going to have to be grown according to a lot of very similar laws on different molds, and a lot of our computers of the future will have to be grown and built on this type of science, and it's all based around crystal science. So I have I have a picture. It's called Cubes in that folder. If you want to bring that one up, and and there's also one right at the beginning. But this Cubes picture, let me see if I can't switch to a screenshot so Ken can see what I'm looking at. But basically, this is the idea of crystals, and the unit cell is always a cube. Generally, the easiest one that can both have all vertices the same, and it will tile the plane. That is leaving no gaps that you could, if you had an infinite amount of cubes. It's one of the few polyhedra where you can have the both you know, like where it tiles the plane and you have the same number of vertices at every corner and stuff. There's also ways to tile the plane with other solid shapes and other types of crystals, like as I explained, quasi-crystals and other types of crystals where all the unit cells aren't the same, but most things tend to be cubic, or tetragonal or orthorhombic or monoclinic or triclinic, one of those types, because those unit cells have to be able to tile the plane in 3 dimensions. And I just think it's really interesting that a lot of these generating functions, which create these really weird crystal patterns based on the different types of, it's basically whatever the atoms are in the material, and the covalent bonds, those electrons on the outer shell, whichever way that they have a certain type of symmetry, they're going to bond and create bonds at those certain angles, which, oh, it's so weird that those laws which happen on the quantum mechanical level translate on the macroscopic level as they're built upon many of these things, many iterations or many steps or sequences of collection of these types of things, like just the way that, like, I have a lot of pictures of snowflakes in here that I put in too, just to sort of use that analogy. As a snowflake forms, it's forming this hexagonal symmetry and sort of building off of that in out in 3 dimensions, and sort of these things are based on these matching rules, again similar to the matching rules that he sets up in that book. But as you iterate them over time, and as you grow and expand the crystal, all these little random arrangements turn into different they add complexity. That's why you can have a million snowflakes fall and no two are exactly alike. You have all this randomness and these differences that are created through these random generations, but yet they all obey those simple fundamental rules for matching and the bonds that they create, because they have to have that symmetry again, and that's based on what those atoms look like on the atomic or quantum mechanical level, the interactions that they have with those outer electron shells. And a lot of the science of the future is going to be dependent on people understanding and knowing those building blocks and being able to build different types of crystals and different types of structures out of them. Because a lot of the materials and things of the future probably could be built out of scaled up versions of things built on atom by atom. I have a picture in here called Fractal Machine that's really interesting. It's the idea of these fractal crystals that could be used to build little tiny machines out of atoms, and that's going to be the future is of all this technology and stuff. And but more importantly, it's not just going to be the future of our technology, but I think it's going to be the future of physics, and the physics that we're going to need to really unlock the true nature and the true secrets of how this universe is constructed, and find all those other neat things that we're going to get more into detail with Ken in part 2. But I don't know, Ken, did you have anything you wanted to say about the whole idea of how fractals are related to crystals, and fractals are related to just this idea of generating functions that can create things that we see in nature through very simple 1D 2-bit arrays that he was generating most of this from. Very simple one-dimensional 2-bit systems,
Yeah, exactly. When I was an undergraduate student, my professor was working on something very similar, and what he called it simplicial quantum gravity, where a simplex is what you're describing. It's basic unit of geometry, like a line or right or a triangle or a pyramid, and up to structures like that multidimensionally, and that you can construct space-time based on these unit cells, which is exactly what Stephen Wolfram is pointing at in what you're saying. And there's another physicist, namely Renata Lal, at University of Waterloo, who's doing the same thing with gravity. And what they found, especially Renata, is that indeed, that the dimension of space is a fractal, meaning that it's not an integer, it's not 1, 2, or 3, it's 2.93. And so how she gets that is what you're talking about, where you take these unit cells, and what Wolfram was talking about, we take the unit cells, and after putting them, a large number of them together, effectively the dimension looks like an average over all of their little structures, and that dimension is a fractal dimension. And so fractals also have this curious property of what you might call replication or self-organization or self-duplication, where on higher levels, where you've used trillions and trillions of them, you see this structure that looks familiarly like the smaller structure, you know, and we see that as well in physics. So yeah, with respect to crystals and crystallography, it's a sort of a brilliant breakthrough in our understanding of, you know, of how do we take the information that we get from crystals and put the crystal back together again. So, for example, when you have light shining through a crystal, right? It scatters through the crystal. It gives you a wonderful pattern on the wall. Then you have to take that pattern and try to figure out what the crystal was that generated it. And so this becomes a much easier task when you're using these generating functions. But really quickly, I have this little thing. This, I'm not sure if you can see that, but this is a generating function. And you had that on your wall before.
Yeah.
It's essentially a really simple thing. It's a function which is the sum over x to the 0, x to the 1, x squared, x cubed, etc., with coefficients in front, with numbers in front. That's all it is. It's a simple polynomial. And yet, from this entity, Wolfram, myself, Lal, so many people are saying you can generate almost anything you want to see in nature. In fact, this structure looks like a computer code. Why? Because the first element of the structure, you can say that the x to the 0th power kind of represents the first line of code. And the value, when you're writing code, every line of code generates a value, right? So you say x equals 1, that's your first line of code. So the value of your first line of code is 1. And maybe your next line of code says, take x equals 1 and square it. So that next line of code produces 1 as well. The point is that each one of these coefficients represents the outcome of different lines of code. So there's a direct connection between the generating function and computer coding. And this is as simple as you can get with computer codes. Okay, it doesn't get any simpler than this. And this is exactly what Wolfram is talking about when he's saying, you know, computer science is able to do physics and math in a very different way, an algorithmic way. And the algorithm is this generating function. And the outcome, you know, each line of code produces an outcome. That's all in the generating function. That's all in the coefficients. Those are the measurables, the outcomes.
What I always found interesting is that certain symmetric patterns too in function space, which is what that equation is in a function space, describes, is things like sine waves. When you plot those out in that function space using like a sine wave, it kills all the odd terms or the even terms, like the cosines.
That's right.
It's like the same thing. It kills out certain terms and then has certain values in front of all those terms. But it's so weird how it shows symmetry when you have those things in nature that are symmetrical, like sine waves or cosines, and how that function changes depending on those.
And what you're talking about sort of in general is we would call that an even generating function, where all of the even terms stay and all of the odd terms magically disappear, vanish to zero, and an odd generating function, where the reverse, where all of the odd terms stay, x, x cubed, x to the fifth, and all of the even terms disappear. And these two entities, you know, you just add them back together, you get one big generating function. But these two entities are exactly what you're talking about. One represents what we call a sine wave, and the other represents what we call a cosine wave. And so all of a sudden you have this strange way of looking at trigonometry, right? And thus that gives you another language for investigating crystals, for investigating these underlying patterns. Because just to let you know as well, I sort of told you what that means in terms of computer programs, but you can just say that x to the 0 or x to the first power is just some structure. One structure we call x to the 0, another structure we call x to the 1, whatever. It's just a pure math way of talking about structures. Maybe the size of the structure, or maybe it's the color of the structure, or maybe it's the speed of the structure, you know, or maybe it's the dimensionality. It doesn't, you know, however you choose to define it, then these answers, these coefficients, tell you what you should be measuring. You know, if you measured this structure, these are the measurements. So yeah, it's quite profound that it's taken us until the 1990s to actually start seeing this. Like, okay, this is a tool that we can actually use in nature. This combinatorics, these generating functions. And this is what Wolfram just sucked up and said, my God, this works. This absolutely can tell us so much more about computer science, and at the same time, it looks exactly like reality. Now, if there isn't a bigger... Yeah, sorry.
Similar to what Garrett Lisi did with the E8 structures and saying, hey, this kind of looks like particle physics.
That's right.
And finding these structures in mathematics that mimic or mirror structures in physics.
That's right.
Or spit them out as results.
Or spit them out as results, exactly. Oh, and the funny thing, you mentioned, you know, Garrett Lisi. It's not about Garrett, but it's actually about Richard Feynman. The whole idea is that the basic mathematical structure looks like, you know, reality. And so with Feynman diagrams, they're a generating function. Feynman diagrams, the Feynman perturbation theory method is this. It is a generating function with terms like x, x squared, x cubed, x to the fourth, and each one of the coefficients is a measure of virtual particle interactions. Okay, so when you're trying to figure out, you know, how do I calculate something in quantum mechanics using Feynman diagrams, you're doing a generating function. You're doing this program. And you're right in saying that Garrett Lisi's system is very similar to this. It's that whole notion of taking this E8 by E8 geometry and seeing the evidence of quarks and seeing the evidence of leptons or electrons in it. So absolutely.
Yeah, there's just something weird about this fractal that is space-time, that at this one-dimensional limit, like Planck's constant, the Planck length, and that fundamental unit of distance, that's like one end of the spectrum, and then at the other end of the spectrum you have the scale of, you know, all the way to the end of the universe, you know, as far as you can go, you know, like unfathomable distances. Out into space. So it's really interesting how the laws of physics just change depending on, you know, like what size you're looking at, and you know, and how they're very consistent over a certain realm of like classical dynamics is very good at explaining things within our realm of physical reality. You know, classical mechanics, so normal speeds, normal distances. Things that we encounter every day on our normal everyday life. But then when you start shrinking down to these Planck lengths or these quantum distances, the laws of physics suddenly break down and turn into something else that doesn't really look like it makes sense, or doesn't make sense according to how we can measure it and the questions that we can ask, you know.
Right.
as Heisenberg said, it's not the universe as it is. It's the universe responding to our line of questioning.
That's right. That's right. And sort of how I believe, how my work says that that kind of comes about is the notion that it's a basic concept in combinatorics, but in essence, it's how do you take a space and just choose to divide it, okay? It's called the interior-exterior principle of combinatorics, but how do you choose to take a space and divide it up? Okay, so if you divide it up in a certain way, there are only two parts, and it's like you against God. And if you divide it up in a two-part way, the physics should reflect the physics behind everything. That universe is the whole thing. But if you divide it up into two ways, and maybe there's an intersection between the two, then the physics, if there's physics to it, should look like the physics of you and the whole universe at large, you making measurements. But if you divide it up into three ways, then you'll get some test object that you're firing your bullets at, and then you get the rest of the universe. My point is that there are simple ways of getting quantum mechanics and the real strange curiosities of quantum mechanics out of very simple math. That's simple math, where you just say, oh, I just want the universe to have three things, and always three things. And so you find mysteriously that in that simple math, you get, what we call a potential, a target, you get a projectile, a bullet, and you get a background environment. And you can base all of your calculations on this. So the idea of what makes quantum mechanics so strange and mysterious can also be taken from that. You find that in this way of thinking about it, where you divided the universe into three parts, that you get to determine how big you are, and by virtue of that, get to determine how big the rest of the universe or the environment or the target is. And because you've made those determinations, everything else changes. That is to say, your subjective point of view has determined everything else in the universe, from whatever you're firing at to how the environment looks. And that's one of the basic concepts we get from quantum mechanics.
All right? We're gonna talk about that. We're gonna take a quick commercial break, and then we're gonna get into that stuff and some more interesting stuff with your specific research and work into quantum gravity and in this exact topic. So let's take a quick break from our sponsor. We'll be right back.
Are you sick and tired of being sick and tired?
Yes.
Does the stress of daily life seem just like too much?
Yes.
Are you simply fed up?
Yes.
Do you wish you could just make it all chill out?
But how?
Well, then you need a Royale grinder. Royale grinder is a jumbo-sized 2.5-inch diameter premium 4-piece herb grinder that fits in the palm of your hand, with 50 closely interlined, everlasting chunky teeth that will keep on shredding whatever enters your chamber.
I can use it for all my herbs. Thanks, Royal Grinder. I'll never feel shitty again.
Order now at www.royalegrinders.com. That's www.royalegrinders.com.
All right, and we are back from our commercial break. You're watching Alien Scientist, Science and Controversy Hour on Zen Live TV. We're talking about um, simple generating functions and the idea of kind of behind Wolfram Alpha that he, not Wolfram Alpha, Stephen Wolfram, the same guy who created Wolfram Alpha and MathCAD and these other programs for the computer. His idea of this. That things in nature are created from much simpler generating functions that maybe physics might benefit from looking at things like this too. And in the first half, we did also talk about a little bit about crystals and cells and sort of the idea of crystallization and how everything's the same. That at one point is the same and everywhere else in the crystal, or that the laws for how that one unit attaches to its neighbors is the same for every other cell inside the crystal, and that sort of over maybe there's little differences or variances, but over a big macroscopic number of times you zoom out and you'll find that there are these symmetries that reappear on the larger scale, even if they're not always held on the smaller scale. And also, I wanted to touch upon that before we go into the other topic about how important it is in a lot of the futuristic crystal technologies, even creating better anodes and lithium-ion batteries, battery technology, solar cell technology. All this stuff is going to benefit massively from super purity of materials and being able to build things on the atomic scale and make sure that all those atoms are lined up exactly without any mismatches or defects and abnormalities inside this crystal structure, because those sorts of abnormalities can affect things really greatly. And just with what we've talked about with metamaterials and a lot of the other things, that the structure of things on the atomic level have a lot to do with its physical properties, so that if you're able to build things more exactly on these minute structures, it's going to lend a lot to the future of our science and the things that we're going to be able to create through these types of machines. Also, cellular automation, building self-assembly, nanorobots, things like that. The whole future is going to be based around many of these same principles that are. If this is in reality what is generating the generating function for the universe that we exist in, say that there's some not necessarily what's in that book, but something else that could be the new theory of everything, that's going to be the next breakthrough in theoretical physics. You'll be the next Einstein if you come up with this, and this, I believe, is the direction that it's going to come from. It's not going to come from CERN or looking at particle interactions or particle physics. It's going to come from someone who's going to step outside and be like, well, are thinking things of in a very mathematical nature to say, all right, well, I'm going to create the generating function for the universe. That this is the computer program that's running on some alien mainframe server, that we all live in this game world on some alien mainframe, and that our entire universe is based on this generating function. And as long as you have that generating function, then you can go out and build your own computer and build your own universe inside of that from this code, or do lots of other things depending on what the laws of physics that it spits out, or what we'll be able to learn from such a theory of everything, or such a generating function for the universe. So lots of really interesting stuff. A lot of different comments that people are engaging in a lot of thought-provoking topics being discussed on the shows here, and I'm glad to get into this kind of stuff, because I really enjoy talking about this type of stuff, but it's just hard to sit down and write up a interesting thing on my website about it. I've tried before with the Zero Theory page I used to have and stuff, but it's much more interesting just talking about it in terms of what we can learn from physics and the nature of our universe with it, and also all the technology that's going to come out of this exact type of science, and understanding the importance of small-scale interactions and just building everything to this state of perfection that's going to need to be required for a lot of our future technology in order to get things that don't break or don't wear out, or computers that run off of sunlight and don't need batteries that run for much longer than normal batteries and need only a quarter of the charging time, and all those types of technologies, which are going to be so important in the next 20-25 years, are going to come from this. And also, even even I talked about this before, but in the last week's episode with I keep bringing up cold fusion and cold fusion technologies, but there was a couple really great speakers at the conference in March at the colloquium at MIT, who were talking about building fractal crystals and using these types of this type of fractal self-assembly crystals to build cold fusion reactor cells, because there's lots of things that they were talking about that increase reaction rates. For one thing, surface area seems to be a key thing. There seems to be some interaction with the surface plasmons that are interacting and these super waves that happen within the surface plasmon resonances that create this reaction that bring these, push these atoms close enough that through tunneling they fuse, or whatever the case may be. There's some physics going on there, and it has to do with these key things which have been identified and talked about in books like Edmund Storm's book, which I'm reading now, and a couple other books. In fact, I have an extra copy of that book, Ken. I might send that to you so you can read that as well.
Great, thank you.
It's one of the premier top texts on the topic. It doesn't claim to know how it works or give theory of how it works. It just says this is all the observed experimental data. This is what we've got to turn it on. This is how we know it turns off. This is what we know. This is what we don't know, and this is the next step that we need to try and figure out all this out and put the pieces together. But I thought that this stuff, kind of the same kind of science, is super interesting, but also super important for building the technology of the future. And I had a couple pictures of leaves. I was looking at a leaf earlier today, and just on the back of it, all the veins and all the capillaries inside of a leaf, how it has that distribution system for the water and nutrients inside the plant. And it's very similar to a human cardiovascular system, where you have networks of veins and capillaries and arteries which interchange with one another to have the whole oxygen exchange program that is in your body, pumping blood through and exchanging oxygen with your cells, and also taking waste products away. Those types of things, that's also could be created with a generating function that has to have these veins, and then you have to know that the width of that vein has to have the volume of blood flow, so that it's not going to have too high of a blood pressure in that particular capillary or artery or whatever have you, and you have to make sure that there's all kinds of rules there, very similar to the rules that they set up in some of these 1D array generating functions. There's rules there that have to follow on the physical level in order to build systems with that. And think about the nanotechnology that you could build with trying to copy, even the human body or the venous system. You could build a spacesuit that has a temperature regulation system that pumps fluid through the skin of the spacesuit using venous capillary type systems, and it could all be built through self-assembly or through a 3D printer that uses these types of generating functions to calculate where it needs to build what, and where it needs to leave a gap, and where it needs to have a space, something there. So
let me also put in that the idea of resonance is in fact very similar to the idea of a generating function. And so the idea of resonance is when you create these small structures to build a big structure, will that big structure stay put together, right?
Yeah.
Will your Lego blocks, when you build, a space shuttle from them, actually not, will it stay together, or will it fall apart, and how long will it take? So the idea is that the structure's stability can be looked at as a resonance of the structure. And the resonance comes about on the small level by, again, how have you constructed? Okay, so I guess what I'm trying to get to is...
Well, I saw an article recently that this reminded me of this graduate student wanted to figure out the ideal place to put his Wi-Fi router in his house. So he just simply solved the 2D Helmholtz equation and put the dimensions of his apartment as the boundary conditions, and found this was the ideal place to put his Wi-Fi router. And I thought that it was very similar to what you're saying, that you have these functions and all these different frequencies that can interact over things, and you solve that simple resonance equation to find out where those resonances are and where the sweet spot is.
Exactly. And so, in a sort of a glorious big way, all structure can be viewed as a resonance. Okay, so a resonance of simpler building blocks. All structures, and by the way, the reverse can also happen. Any structure in nature, and I used to tell my students this, and that blew their minds, but any structure in nature can be ripped apart if you know its resonance frequency. So if you know the frequency at which this thing resonates, and by the way, all structures in the universe have a resonance frequency, every last one.
Yeah.
Whether it's the atom, or whether it's you, or whether it's water.
Molecules that you want to.
Right, exactly. San Francisco, they all have resonance frequencies. So if you know the resonance frequency, you can do both things. You can either destroy it, take it apart, or you can put it back together. This is the beauty of that underlying idea, and this goes back to Tesla, but it predates Tesla by hundreds of years.
Yeah,
okay?
People knew that before Tesla, like
absolutely.
Volts, all those other guys that created the math, and that's where differential equations first started coming from, because they realized, oh, we need a math that can understand, well, there's an imbalance here. I have a mass on a spring that when I displace it, it has a force trying to bring it back to equilibrium, but it can never quite get there, and then you have oscillation. Well, how do I describe that with math? How do I calculate?
And by the way, that's what quantum mechanics has sort of demonstrated to us as well.
That's Schrodinger equation. That's what Schrodinger is all about. That's it.
Yeah. That is it. That's why chemistry exists. Why electrons bounce from the ground state to higher excited states, etc. Those are all resonances of the interaction between the electron and the proton.
Right.
Those are the correct resonances.
It's the potential and the kinetic, and it's either in the potential or in the middle. It's all kinetic because it's going to this side, but at either end it's all in potential, and you have some sort of mix between those two, and then you get these resonances and these structures. And that is our universe. And
that's our universe, right? We were able to actually describe the whole freaking thing in terms of resonance. Why is the Earth going around the sun at the distance that it does? Because when the solar system was being created, a resonance effect occurred at the distance that we are from the sun, such that there was an accumulation of matter forming, sort of a seed formed and then bigger and bigger and bigger. And then eventually the planet began to spiral around the sun, technically, but around the sun at a certain distance, the resonance distance for that size object at that particular speed. It's a beautiful thing.
But it's interesting. Resonances are also based on balance, and
that's right.
This idea of balance. And nature is very, very much the yin and the yang, the balance. The up and the down, karma, the good with the bad. I think there's so much of that appears in other places, not just in the physical realm, but even in phenomenology and even in our own daily interactions in our lives. And our mood from day to day, it can be like an oscillating function in some cases.
That's right. And then of course, sorry.
It's really interesting that this balance, this whole idea of balance that you have anytime you have an oscillation, it balances, it oscillates about an equilibrium point. There is that 0 point, and if you were to take away the potential or the kinetic energy, it would just stop and rest at that one balance point. And that everything sorts, even our math equation, all of our math, it's based around what? An equal sign. An equal sign is the balance. It says that the scales are balanced. These two things are balanced. They're equal. It's just all of our mathematics, all of the universe seems to be based on this intricate balance. But things get tipped off the scale, and then sometimes they just stay that way, or they go off into infinities, or sometimes they oscillate and go back and forth and up until a certain point.
Yeah, Newton called that, his third law of dynamics, which is that, equal and opposite forces will balance each other. So whatever's happening, on the one side, it's going to be balanced by a set of forces on the other side to basically keep everything in that natural state of equilibrium. So I was going to mention that in particle physics, when you go to the Large Hadron Collider and you're looking for the Higgs boson or whatever particle you're searching for, what you pick out of the data are what we call resonances. So even the math at quantum field level, theory, discovery stuff, all we're looking for are resonances. And for us, a resonance means you have a particle. You have a stable energy structure, and thus we can name it and we can describe its properties. It's what we call a particle. It is a profound thing, and Wolfram is, from my reading of some of his work and from understanding his similarities to my own stuff. But essentially, Wolfram is saying, look, we have a whole way of describing patterns in nature. So if we just match up our mathematical patterns with the patterns that we actually see in nature, then maybe we've got something. Maybe that's the way we should be doing theoretical physics, or maybe this is just a whole new, different way of doing physics. But what it allows us to do is to create an understanding of the universe, not simply because we just decided to dream up superstring theory, but because we see that there's a pattern match. It's kind of like when you're walking in the crowd and you're looking for someone, you're pattern matching, okay? And sometimes you make a mistake and you go up to the wrong person, but sometimes, most times, you'll get it right. You're like, I know that person. Same thing here, that the generating function is the system of patterns. It is the system, whatever your system, whatever, patterns math says should exist, right? Then you just take those math, like the sine wave or the cosine wave. If you just take those patterns and then you look at nature and say, where do those patterns exist? You go, oh my goodness, they look like light waves, right? Oh my goodness, they look like, solutions to Schrodinger's equation, for atomic blah, blah, blah. And so that's what he's really advocating here, and I think it's the next, as you're saying, it is the step forward for physics, for math, for algorithms, right? Because when you're doing that, again, as I've told you, you're creating an algorithm, you're creating a computer program that is telling you two things. It's telling you about math and it's telling you about nature simultaneously, and you get to test it out. Sims and all of those other programs allow you to see, whether, or, automata allow you to see whether or not your patterns actually seem to give you real stuff. Do people seem to behave on the computer level? So in essence, also what Wolfram is talking about is the matrix. And in the last, I think, 15 years, people like Sylvester James Gates Jr., my dissertation advisor, and other people are now beginning to say, oh my God, the universe is a matrix. It is behaving exactly like a computer program. Oh my goodness, superstring theory is bearing this out. Okay, and so that's what he's advocating, is the matrix concept of how do you approach the universe? How do you approach, And if he's right, and I absolutely believe he is, then whatever program you can create here and on paper, you can find a way of actually creating it in actual nature. And by the way, there's the two computer science guys who created this whole sort of systematic thing we call combinatorics, or analytic combinatorics, one from Princeton, the other from France. But essentially what they did was to codify what he's talking about, to literally say, look, these are the first principles of it, and this is what they do. This is all of the math that you can formulate from all of this way of thinking, from just the ground level. And we
so, yeah. Like, for example, he creates those math functions which create these shells and stuff.
Yes.
The seashells, but it's not necessarily the same algorithm that seashell is using to create its own its seashell. That snail is using to create its shell. You know what I mean?
Well, right.
Some of the same patterns on, like, he's got this one textile cone that has the same thing that look like the pyramids in its shell pattern. Even it's following a function to create the shell pattern, but there's also some sort of thing that's generating its colors and its color schemes on it. I thought that was interesting as well, because there's so many things in nature that, I mean, they're following some sort of primordial rule or some sort of fundamental rule, but it's not like they understand the math. They're just doing it through some other process of self-replication, and in the process of how they grow or expand as an organism. It's sort of built. And I think that understanding DNA is going to have to do so much more with tinkering with these sorts of things. I mean, because what we're doing now with the playing around with DNA and splicing this gene from this thing into that, it might not do the same thing in a different organism, because the symmetries and the resonances, again, those might be different. And
that's right.
And if you're not understanding those and incorporating them into your scientific understanding of what is going on there, you're going to have tragic mistakes and Frankenstein and stuff.
That's right. So your dolly is going to die in a year, even though she's a sheep and she should have lived for, I don't know how long they live, but it's more than a year. You know, so yeah, that's exactly right. The idea is that we are haphazardly throwing DNA together. I mean, don't get me wrong. There's some people who have greater understandings. You know, the guy who decoded the DNA sequence has, you know, obviously a very good understanding of what the hell he's doing. But we're still, you know, not really using some underlying, really core principles like resonance or as you're saying, or Wolfram is presenting, cellular automata ideas that will enable us to really understand what's going on here. How do we really put together, you know, this sequence of DNA in order to combat this virus? How do we really do that, as opposed to just throwing junk together and seeing if it sticks? Because yeah, it's obviously a bad way to build a house, right? You'd like your house to stand for more than a moment. And if you just throw stuff like nails, throwing it at wood and then throwing the wood at insulating material, it's not going to stand for very long.
Well, let's look at like we're like primitive cavemen messing around with alien technology almost in a certain way. It's kind of like the cargo cults where they see these people do these weird things and they go out trying to replicate them to get the same results, but they're just sitting there with a wooden plane on a runway in a field thinking that there's going to be magic birds dropping cargo down on them. It's a very similar idea to that, and that we're toying around with these the structure that we have no clue about, really, its complexity. And there's only one way to learn, I guess, trial and error, but that's how I taught myself, like HTML and other computer programming. It's just like, well, all right, I'm going to change this and see what it does.
That's right.
You know, like, oh, that did that. Okay, so that's what that does, and you know, but a very sort of trial and error process. It's much different than, you know, genetically modified organisms that have been created through selective breeding and stuff. But that's a whole other topic in and of itself. Getting into all that whole debate, and it's a lot more biology than physics, even though there is some physics to be understood there. But I definitely think there's a lot more that can be said about that whole issue in general.
Oh, definitely.
But again, but this is mostly about just the idea of these sort of generating functions, that there is an algorithm or sort of a simple rule. It's just a simple rule. There's some rule that this has to be this and this follows this, and as long as you have that in that order, then all of a sudden these patterns just emerge. That's sort of how he stumbled across this whole thing. He was just like, oh, I wonder if I do this, and oh, let me do 800 iterations and see what it look. Oh my God, look what it's like. How does that happen? You know, and I don't know. It's just fascinating. It just fascinates me to no end, because there's so much stuff in nature that looks like this. There are these fundamental rules, or there's these fundamental laws of physics, and maybe they produce the laws of physics that we see and as we understand them, but maybe they aren't quite as such. There might be something different, more fundamental, that we're not grasping, we're not seeing.
That's right. Picture. That's right. And I think that's exactly, you know, why we probe into the idea of quantum gravity, is because we're looking for something beneath space-time, beneath energy as we know it. Something that will enable us to just not just get those things, but get so much more understanding out of it. And so,
why is a proton the size of a proton? Why isn't a proton this size?
And why doesn't it decay? Right.
Right.
But which is, by the way, one of the problems of superstring theory and of almost all of these theories out there, is that they predict proton decay, and we've been measuring that since like 1977. So we should have seen a proton decay every year in these giant vats of water since 1977, and we have not seen a single one, which then leads us to believe that the proton decays in like 10 to the 42 years. That's mind-bogglingly stupid, okay? I mean, you know, the bottom line is that there's no evidence for it, and yet we still have built theories around the idea that it should exist. And that, again, that's what superstring theory gives us. So what we're saying is that if there's something more basic to what is space and time, what is energy and matter, blah, 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 maybe it will provide for us. The proton's stable. These structures look like quarks, right? These structures look like electrons and whatever, and their interactions work in the way that Wolfram is talking about, with some sort of simple algorithm. That if I put this here, it's just going to decay. Or if I put these two together, they'll combine and form this new structure, which looks like, I don't know, a neutron, who knows. But, so maybe the underlying mechanics of all of the physics that we see around us is as simple as cellular automata, or as simple as what Wolfram is saying.
Monadular automata.
Yeah, monadular, exactly. And, and from my perspective, we call this a complete network. That's the monad concept of Leibniz, which is that everything in the universe, no matter what you think those things are directly connected with each other. It's a very astonishing principle.
Yeah, I think that's. I mean, I'm glad I wanted to do a whole hour-long talk on this. I know maybe it's kind of boring in some places for the audience, but it's a topic that I definitely think needed to be covered, or at least talked upon. I mean, there's the amount of detail we even went into on the show is just barely scratching the surface. I mean, you could go into this stuff, and really the only way is to really get involved and start playing around with it yourself. And if you're interested in doing that, there's an iPad app. I think might even be on iPhone as well. But check it out, A New Kind of Science, and look for that in the App Store. I saw something about it, and start playing around with some of these. Create a bunch of rules, and then you can spit out whatever it looks like, and see what you can come up with.
Yeah, create your own universe.
Yeah, create your own whatever function space, I guess. I don't know.
That's right.
It's not quite a universe yet, but hey, this is the baby steps. We're gonna get there,
That's right.
Everyone's got to start somewhere, like you can't just jump in and create, just go and create universes,
Right.
you gotta know what you're doing first. But anyway,
although Stephen Hawking would like to do that.
Yes, he would. I would like to see him do that. But yeah, I'm glad we got the chance to at least scratch the surface on this topic. Again, any one of the things we mentioned on the show could be gone into in exhaustive detail. But
that kind of stuff.
Yeah. Oh yeah. I got lots of different awesome pictures here that I hope they showed them during the talks throughout. The fractal broccoli is one of my favorite. The broccoli that has those fractal structures and stuff. Yes. But anyways, the universe is a fractal where you have to figure out what's generating that fractal. There's some generating function, and the physics we're doing now, we're just basically looking at the Mandelbrot set and trying to measure things and figure out rules to those measurements. That's our physics. We're shooting in the dark. We're not seeing the concept that's the generating function that's producing this universe, and that's sort of the concept that I really want to hit home for people in this episode and get them thinking about. So we're out of time, unfortunately, for today, but join us next week and feel free to call in 4 to 5 every Saturday, and love to hear from you. I'd love to get some questions and answer some questions for you. And once again, my guest, Ken Griggs, thank you all for watching, and take care. Comments and questions, we're more than happy to answer in the comments below. Thank you.